I'd like to talk about terrain in digital elevation models in GIS. Terrain's important because, well, mass flows downhill, water accumulates in low, flat areas, and if we're going to modify the environment, we need to know, in many cases, what the elevations or heights are. Now, we typically store and work with our data in a grid structure, in a raster structure. Now, we can also store terrain data in contours or in TINs, triangulated irregular networks. I've talked about those before and will again briefly later, but for the most part, our bread and butter are rasters. We have elevations in each of our raster cells. Now, these elevations imply a height, so if I were to visualize this Z or third dimension across the landscape, you could think of a bunch of cells that are kind of draped across the landscape with the cell centers where these Z values are given. Now, the raster usually corresponds to the directions of my Y and my X coordinate system, so they're going along the grid north, south, and east, west. And I can think of this raster facet up on the landscape as having a direction, a normal direction, that's at right angles to the surface, and that's not going to be the same as the direction straight up and down from my datum up to where my surface is. And with that normal direction, I can calculate slope and aspect and other raster attributes that are important for terrain. Now, I calculate those using the Z values and differences between these Z values. So I have Z7 to Z0. I can calculate the difference in elevation between C7 and Z0, or Z8 and Z5, any of these. So I calculate it as this value minus that value, or vice versa. So the Zij, a delta Zij, is a Z5 to 8 here, is the height at 5 minus the height at 8. So in this case, 955 minus 942, or 13. And we use these delta Zij's to calculate many of our terrain metrics, things like the slope amount or the aspect, which is the slope direction. A bunch of things we can calculate. Those are described in the text in the reading, so take a look at those. As an example of why terrain matters, the two most important perhaps being slope and aspect, we often want to know how steep the road or path is, or how aspect varies across the landscape because it has real impact. Am I going to fall and break my neck? Or where is there going to be snow late in the season or at a particular time I want to visit a location? What's the insulation? So a good example here of why terrain matters is shown by the Sutter Buttes, a small volcanic cone in the middle of the Central Valley in California, north of Sacramento. It's near the other twin cities, Yuba City and Marysville, two little towns that are about the size of Hugo and Fridley, north of Sacramento. So the Sutter Buttes are this area of arid hill slopes in a flat agricultural valley, much of which has been modified as it can be for irrigated agriculture, here rice, growing it in the desert, but also for wine grapes or for other grasses or wheat or things around it. So here terrain matters and what you can do where. It also affects the natural environment in that we have the landscape here in this three-dimensional perspective view. This is actually from a high-resolution satellite. You can see that on the north slope, where it's shady, where there's less sun and less summer drought, trees can grow in abundance, whereas on the south slope, mostly grasses, which can go dormant during the long, dry, hot summer when there's a lot of sunlight on these south-facing steep slopes and not much water. The grasses can survive through that. They go dormant underground and resprout when there's vegetation. They just basically lose their leaves. So here on the south, we have mostly grasses, and here on the north, we have mostly trees. So slope aspect of the terrain variables are important for lots of reasons, including the distribution of energy and mass across the landscape and how it structures vegetation or human activities. Now, we measure slope and aspect actually in two ways, but slope we measure in percent and slope again as degrees. So percent is basically the change in a horizontal distance with a change in a vertical distance. So I can look at how fast I go up in a distance that I go horizontally. If I'm going straight down, it's negative infinity. I'm not moving any in the horizontal direction, and I'm going a lot in the vertical direction. Straight up is infinite, and in between, I get numbers that vary from 0 to infinity. I can get percent slopes that are greater than 100%, because if I go up 2 for every 1 I go over, that's 2 to 1, or as the formula will show, a 200% slope. You can also measure as degrees, and degrees go from 0 to 90. Actually, I'm sorry, from minus 90 to 90, from up to down. So here's a clinometer, and you can see it's graduated along this from 90 to 0 and back to 90 again. And I have to know whether I'm pointing down or up to identify whether it's a plus or a minus 90. So the slope calculation is pretty straightforward. It's in the book. We show the rise over the run times 100. If our rise is 10 feet, that is, I've measured this distance that I've climbed up. And I've gone from this point at the down here to this point at the along the hypotenuse. So I go along this slope. I go up a distance A and across a distance B. So my rise here is 10, and my run here is 40. So the slope is 10 over 40 times 100, or 25%. Now that's actually a steep slope. Remember, most roads are constructed to be below 6% slope, or in extreme cases 8%, at least most highways. Small back roads can get 20 or 25 or 30%, but those are rare. So this slope as a percent is this 10 over 40 times 100, or 25%, or as a angle, it's the inverse tangent of 10 over 40, or 14 degrees. You got to be careful, because tools like Excel report the slope in radians. When you calculate the arctan, you get an output in radians, which would be a number like 0.24497. That's not the slope in degrees. You have to multiply by this factor, 57.29578, and actually it goes on, but that's good enough for us to get the slope in degrees, so be careful. Another thing you have to know about is that when calculating slope, we report it at a point at that cell center, but we have to measure it over a distance, so we can get different values because we can measure over different distances. For example, we might ask ourselves, is this guy crazy? You might say, no, I mean, there's a really steep slope here. It's only about 45 degrees or 100%, and heck, when we were kids, we all took bikes down things like that off the nearest hill or slope, or if we didn't have that, we'd build a ramp in our driveway, or some of the more inventive of us would maybe go off the roof. But if you go off a cliff, I mean, like this point right here, now that, you got to be crazy. So we can calculate the slope, but remember, it's centered on a point across some distance. So here I have two distances that give me different relative height changes, and so I get different slopes at the same point. So here in this yellow, the rise is 29 feet, more or less. The run is 30 feet. So the slope is 29 over 30 times 100, or 96.7%. That's a pretty steep slope, but, you know, it's not going to kill you. Whereas here, in the blue, over this shorter distance, the run is only 2.3 feet, but the drop is 9 foot. The guy's going to go off this little cliff here. So that slope is 9 over 2.3 times 100, or 391%, a big difference, because we're going across a different sampling area. So any slope calculation has to be accompanied by the conditions over which it was calculated. You have to give the distance. So the grain or the cell size is going to affect the slope that you calculate, and how many cells you jump across to measure the slope is generally going to give you a different value. Now here's a question for you. In general, as we increase the distance, what happens to the slope values over an area? Do they become bigger, smaller on average, stay the same? How are they distributed? So something to think about. Okay, so we also have to be careful in the direction in which we measure the rise or run. So here's two directions. This one is I'm measuring it down here along this point of steepest descent. And here I'm measuring it across the face of this slope. So clearly, if I measure in my steepest direction, it's the same calculation as before, this 391%. But if I'm moving along a contour across a level here, I get 0 rise and a 7-foot run, so that's a 0% slope. So the idea is that we have to be careful of the direction in which we measure slope, and typically we report the slope in the steepest direction downhill. So you have the steepest downslope direction is the slope that you report. You don't want to measure at an angle other than the steepest direction. Well, it's pretty easy if I can lay my tape in any direction or here calculate what the steepest direction is, but I have a coordinate system that gives me these raster cells, and the slope doesn't always fall along the axis of these coordinate cells, so I just can't calculate the elevation at one cell and the elevation at another cell and know the difference between those cell centers and get my slope, because I'm moving at odd distances. So I have to factor that in. If I look at it from above, this might be the direction of my steepest decline and slope, but I have to somehow get the elevation averaged across these cells. I have to use those cells somehow. Well, we've come up with formula that use moving windows that basically do that weighting in the calculation. And this formula for slope is the inverse tangent of a change in z with a change in x squared plus a change in z with a change in y squared, all taken to the square root, and then we take the arctangent of that. Now the moving window looks something like this. So we have again our z zeros, and we're looking at the top of our set of cells. And we have general formulas to calculate our delta z in the y direction and our delta z in the x direction. So our dz dx, or delta z delta x, is this thing, and our dz dy is this thing. So we're calculating then the slope of these using various combinations of cells. Now all our examples show 3 by 3, and most do, but some use more than the nearest cells, the cells touching the center cell. Then we assign the slope value to the center cell. Well, how do we do it? There's this one called the nearest neighbor, and all we do is basically take the distance across the two adjacent cells. In this case, we're going to take z5 minus z4 for the dz dx, so this is the x direction, and the z2 minus z7 for the dz dy. Now we have to divide that by the cell distance we travel. In this case, if this cell is 10, we're going across 1, 2 cells. So we calculate the distance as 2c. So this is a change in the z with a change in y, or a change in the z and a change in x. And we can do the calculation here to get the values and then plug it into our formula, the inverse tangent of that dz dx squared plus dz dy squared, all taken to the square root. And I get a number here of 25.3. Now there's another method we could use besides this for nearest neighbor elevation values, and it says, well, I don't want to just use the primacy of these two, showing a kernel like this, a 1 minus 1 and a 1 minus 1 in the two directions. I want to look at this combination of all the kernels, but I want to weight these middle ones, all these cells. I'll weight these middle ones. So I can do this moving window where I calculate the zdx, but this z4 gets a value of minus 2. This z1 gets a value of minus 1, and z6 gets a value of minus 1, and calculating our dz dx. All I'm doing is calculating my dz dx a little differently with a weighting of the cells that are on either side of my central column here to get that gradient across the x. Gives me a little different dz dx. Same thing with the dz dy. Again, I'm going to weight the central cell more, but I want to include the weights from these two side cells. And so I'll do that, and I get a little bit different dz dy. The formula is the same in all these cases. I just have different input. So I get this 0.39 squared minus 0.16 squared. Take the square root of the sum of those, and I get a slightly different calculation for the slope. So the thing you got to know or got to remember is that not only does it depend on the number of cells and the size of the cells, but the weights that you give these cells. And there have been literally hundreds of kernels and arguments for calculating the dz dx and the dz dy. I'll leave that to you to look at the literature. Really, these two methods are generally among the best, or at least not worse than most of the other alternatives, but there's a rich literature in that. Okay, aspect remembers this azimuth angle from the north. It's typically reported clockwise around from the north. We have a slightly different formula, but it still depends on these dz dy's and dz dx's. Now it's this odd thing, this 180 minus the inverse tangent of the ratio of the dz dy to the dz dx plus 90 over the absolute value to get a sign convention. And so the calculations are pretty straightforward. Same thing, if we use the two different methods, we get slightly different dz dx's and dz dy's, and so that gives us slightly different aspect calculations. But generally, these formulas then can be applied to any raster data set in a standard fashion to give you a calculation of slope and aspect. So that's how we do it.